Welcome to ServoSoft, the optimal solution. This tutorial showcases ServoSoft's powerful optimizer by minimizing the motor torque for the slider crank mechanism. The slider crank mechanism is a complete dynamic model, considering the motion profile, inertia, mass, and gravity effects throughout the entire range of motion. The slider crank is a perfect example to showcase the optimizer doing what no human being can do. Here I have the project loaded with the mechanism data and the drive and motor selection already completed. So now I will go to the sequence form. Let's see what profiles we have in the chart. We have the load distance and velocity for profiles 1 and 2, the transformation distance and velocity for profiles 3 and 4, and the motor torque and velocity for profiles 5 and 6. The sequence is simple. Just one constant velocity segment with one revolution of the crank in 1 second. When I select the crosshairs, the slider crank appears, which shows its orientation and its dimensions are to scale. In this case, we have a 30-degree incline and a small offset. Also note that the transformation distance and velocity are also the crank distance and velocity. As I drag the crosshairs, the slider crank moves, showing its position at that point in the sequence. Even though the crank is rotating at a constant velocity of 1 revolution per second, the motor torque is continuously changing as shown by the motor torque profile. The maximum torque is 4.05 Newton meters at 0.716 seconds. So how can we reduce the motor torque while still completing 1 revolution in 1 second? Let's see what the optimizer can do. What is the optimizer? The optimizer plays with motion profiles to optimize a target value. Target values include time, velocity, accel and decel, jerk, motor torque, and so on, as listed here. There are 3 other key elements to the optimizer: constraints, polynomials, and splines. I'll discuss each one now. Constraints are specified for each move or segment group. In this case, I have 1 segment. The Edit Constraints form allows me to place additional constraints or limits on what is considered an acceptable result. For example, let's say we want to optimize for time. This usually means we need to use more torque to move the same distance in less time. So we can add a motor peak torque margin constraint so that we do not use more torque than the motor can provide. Let's say we want at least 10% peak torque margin. Any results that do not meet this constraint are discarded. With polynomials, we can solve almost any motion profile. From our university days, recall the definition. A polynomial of nth order is a mathematical function of this form. I just want to mention some definitions. Polynomials 3, 4, 5 and 4, 5, 6, 7 are subsets of the full polynomials, but with the first term set to 0. Poly 3, 4, 5 and 4, 5, 6, 7, which have been used in ServoSoft since the beginning, are known as ramp profiles, where the start and end acceleration values are 0. For poly 1 to 5 and poly 1 to 7, which have the first terms, a lot more flexibility is possible. For example, poly 1 to 5 allows the user to specify the start and end acceleration, and for poly 1 to 7, users can also specify the start and end jerk values. What is a spline? A spline is a set of combined polynomials, nothing more. And when we string a number of polynomials together, we can shape virtually any motion profile. Splines are a powerful concept, and as you will see, they unleash so much opportunity for the optimizer in ServoSoft. Okay, now that we covered some key fundamentals, let's get back to our objective of optimizing the slider crank to minimize motor torque, while still completing 1 revolution of the crank in 1 second. The first thing we should do in this case is to make the sequence better for optimizing by splitting the 1 segment into smaller segments. We could use the existing segment, but this limits us to just 1 polynomial. Splitting a segment is easy. Just select the segment and then select Split Segment. And I will select 4 segments. And now I have 4 equal segments, each 250 milliseconds and 90 degrees. In theory, I could split our original segment into 10 or more segments, and we should get better results. But given the number of permutations, the optimizer could take quite a long time to find perhaps marginally better results. So 4 segments strikes a good balance in this case. Okay, now I'm ready to go back to the optimizer. We want to minimize the motor maximum torque, so I will select motor maximum torque as the target value. And I will just select the poly 1 to 5. A 5th order spline of 4 segments will give us plenty of flexibility in this case. In the table, you will see a range of motion profile values for each segment. I can go and change each one individually directly in this table, or I can set them all at once using the Edit Constraints form. I will give the optimizer a lot of flexibility for each segment. First, the standard constraints. I will leave acceleration completely open. Now I will add several other constraints. First, I want the total duration of the segment group to be 1 second. And I want the start and end velocities of the segment group to be equal. I'll set the range between 300 and 450 degrees per second. Here I'll set the start and end accel equal to each other to ensure they are continuous, meaning from the end of the cycle to the start of the next cycle. I'll use a range of -300 to 300 degrees per second squared. Finally, I'll set the segment distance overshoot to plus or minus 50%, and I'll ensure the total distance is 360 degrees. I will click OK to accept the constraints. Next, I will change the step values to increase the resolution of the segment parameters. This slider crank application is quite sensitive, so higher resolution steps can be helpful. The trade-off is a longer runtime. By entering a duration step of 0.00005 seconds, the optimizer will play with the duration values using this step value within the min-max range of 0.05 to 0.4 seconds. And similarly for the other step values and their segment parameters. Now everything is ready, so I will let the optimizer get to work by clicking the Start button. The optimizer will continuously update and show the best value it has found so far, and it will also show failures. If I want to monitor the failures more closely, I can update the results every calculation. But I just want to let it run, so I'll set the update frequency to 100. The optimizer will run for several minutes, so I will pause the tutorial until it's done. Now the optimizer is done, and it found a solution that reduces the motor maximum torque to 1.353 Newton meters, which is a 67% improvement over the original 4.05 Newton meter value. By clicking OK, I will apply our optimizer sequence, and in doing so, the parameters we have specified are also saved with the new sequence. Here we have our new sequence with a 5th order spline of 4 segments. And now as I highlight the motor torque profile, clearly it is a lot lower than before. Recall our objective, to minimize the motor torque while still completing 1 revolution of the crank in 1 second. This concludes the ServoSoft tutorial on optimizing the motor torque for the slider crank mechanism. Thank you.